all based on prime numbers. So you want to generate large prime numbers, right? Public keys generally are of the size of thousands of bits. Maybe it can be hundreds, several hundreds of bits, but often thousands of bits. And so you want to be able to generate prime numbers of the order of 2 to the power 1000, right? So how do you generate this? It's not obvious because, well, how do you figure out whether something is a prime number? What's the algorithm we use normally for figuring out whether something is prime? Somebody can speak up, but this is not a complicated. Yeah. So what do we do? It's too obvious, right? Okay. So what's the problem with the typical algorithms that we use for checking whether something is a prime number or not? How far? So basically, what we do is what? We do prime factorization. Well, prime factorization doesn't help if the number is already prime, right? Otherwise, if it's a composite number, prime factorization is, it's actually a very good technique because it, each time you divide by some prime number, you reduce the number, and very quickly the number becomes small. But if it's actually a prime, then it doesn't help, right? So what you can do is, well, you can try every prime number that are under the square root of the number you're checking, right? So that's another common technique. So if you are given n and you are asked to check whether n is a prime number, you could, check all prime numbers that are less than square root n, and that's a deterministic technique. But obviously, if your number is 2 to the power 1000, then its square root is 2 to the power 500, which is still, way larger than what you can do. Right? So what you are left with are primarily these probabilistic techniques. As it turns out that there is, in fact, a deterministic way to check whether something is a prime number, and I believe that problem itself was solved only in the last 10 years or so. Right? So that there is a deterministic way to figure out whether a number that's extremely large is a prime or not. But for practical purposes, we only rely on probabilistic techniques for generating large prime numbers. And in particular, we start with what is called the Fermat's theorem, which says that a to the power p minus 1 equals 1 when you do the arithmetic modulo p. Okay? Where p is a prime number. Okay? So you need to keep that in mind. Okay? So, well, remember this thing I said last lecture? We said, okay, if you take a number a and you multiply it by 1, 2, 3, and so on, you'll end up cycling through all of these numbers, right? That will never wrap around until it has gone through every number less than p, right? So we can write, and I'm just restating this theorem that I mentioned in the last lecture. Now what we do is we can now take the product of both sides, right? So if you take the product of the left-hand side, then you'll get basically a to the power p minus 1 multiplied by p minus 1 factorial, correct? Because it's 1 times, 2 times, 3 times, up to p minus 1, that's p minus 1 factorial, and then a multiplied p minus 1 time gives you a to the power p minus 1, right? On the right-hand side is p minus 1 factorial, right? So if you just multiply everything on the right-hand side, you just get p minus 1 factorial. Well, of course, you can cancel out p minus 1 factorial on both sides, and then you have the Fermat's theorem, right? So it's not very complicated to prove it. At least once you realize that this is the trick you need to use, then the rest of the proof is quite easy. Now, so how can you use Fermat's theorem to figure out whether something, how can you use it to develop a probabilistic way to figure out whether something is prime or not? So the Fermat's theorem tells you that if a given number p is prime, then if you do this computation, it should result in a value 1, correct? So that tells you that if it's a prime, okay, so the evidence for that can be collected by computing a to the power p minus 1, right, where let's say you set a equal to 2, right, because the theorem holds for all values of a, right, it doesn't matter. So obviously, you would say, okay, to speed up computation, I'm going to choose a small value of a. So let's say I use 2, and then I do 2 to the power p minus 1, and do all the computation modulo p, right, and this can be done fairly efficiently, right, because we said exponentiation can be done by repeated squaring, and therefore in log n time, or log p time, right, or log p multiplications, we will be able to compute this, right. Of course, p being large, well, each multiplication takes some time, but let's not worry about it. Let's just say, let's just count the number of multiplications, okay. So in log p multiplications, we can compute a to the power p minus 1, and you can check if it's 1. If it's not 1, then we know it's not prime, right? So that's the probabilistic technique. Now, looking at this number, what would you say is the probability that something is a non-prime but actually produces a value 1? What is the probability that a composite number satisfies this test? Guess. Of course, I want you to guess. I don't want you to think too much, because the correct answer is something that you are not going to get, and in fact, I can't even say it's correct. All I can say is it's provable. The provable answer is that value is something very different from what you might guess. But what would be your guess? It's 1 by p, right? Because you can see that, okay, if I do a to the power p minus 1, at least a catalyst calculation will tell us the result could be anything in the range of 0 to p, and if I have to get a particular value of 1, then there is only chance of 1 by p, okay? And so that's, so it seems that it's not only a probabilistic algorithm, but also actually likely to be a pretty good test, that chances are that for the different for a composite number, it will actually end up giving you, telling you that it is composite, okay, and looks like it's going to be pretty good at that, okay. And of course, if you want to increase your probability, then you can change a, right? You can say, I did 2 to the power p minus 1, then I'll do 3 to the power p minus 1, or 5 to the power p minus 1, and so on, right? And then you can increase the probability of you being right by simply repeating the Fermat's test multiple times. Okay. So anyway, let's talk about what is the. So that is really how you do primality testing, right? So you basically use you could use Fermat's test as a probabilistic test to tell you if something is a prime. If it says it's a prime, well, you're not sure, okay? But if it says it's not prime, then you're sure that it's not a prime. Okay. So that's the question, right? If it's not a prime, what is the probability that you'll find? Because notice that if you are using prime numbers for, say, generating public keys and so on, you want to be pretty sure that it is a prime number, because if it's not, then all of the properties that you're relying on in public key cryptography fall apart. Okay, and in particular, it's not secure if the number is not prime. Okay, and so you want to have a very high probability, very high level of confidence that something is a prime. So what you really care a lot about is to be told that if something is not a prime, that it is not a prime. Okay, I'm saying this because you might think, okay, from an efficiency point of view, you sort of want to be, you might think differently. But efficiency is not the main issue here. We want to be really sure that when we are told something is prime, that it is a prime. So what we want to make sure is that if it's not a prime, then with a very high probability we'll find out that it is not a prime. Okay, so if you want to analyze, we said, back of the envelope type of calculation is, well, there's only a 1 by p chance we won't find. Okay. But it turns out that there are some numbers called Carmichael's numbers, and they end up always satisfying formats property, even though they are composite. Okay, and it doesn't matter what A you use, but these numbers are quite rare. Okay, so they don't really, at least for now, let's ignore that. Okay, if you look at the remaining numbers, then the only thing you can prove is that there is a probability of half. Right? We're not able to prove 1 by p, but just that it is half. Okay, so yeah, as I said, it's only for half the choices of A. Okay, so I won't go through the proof, but if you're interested, you can look it up. It's there, I think, in your textbook, and it's also there in the notes. You can look it up. So, okay, how do we do primarily testing? Right. So we pick some A. We do a to the power n minus 1 equal to 1 mod n. If yes, then we say, okay, it's likely prime. If no, then we say it's a composite number. Okay? And the idea is that even if you know that it's only 0.5, right, even if the test is accurate only half the time, you can still repeat it enough number of times with enough different values of A and to have arbitrarily high confidence. Right? So 2 to the power 100 or 0.5 to the power 100 is probably quite low, and you are willing to accept that probability of being incorrect. Right? Okay, so in reality though, as I said, what you can prove is this 0.5. Right? In practice though, the Fermat's test happens to be much more accurate. So in fact, if you do an experiment taking, say, the first 25 billion numbers, okay, and apply the Fermat's test, it is actually quite good, and it's able to sort it into approximately 1 billion numbers that are possibly prime, okay, and in that billion numbers, there are only 20,000 that are composites, okay. So the actual probability when you do this, when you empirically compute the probability for the first 25 billion numbers, the probability is something like 2 to the power 2 into 10 to the power minus 5, right? And that's a pretty good accuracy. And as it turns out that if you don't stop at billion, you go to trillion or quadrillion, then this probability of being incorrect reduces even more drastically. Okay. So now that's only a part of this solution because it only tells you whether a given number is prime. Okay, so how do you generate a prime number? Because in many cases, at least again in cryptography, if you are generating a key, you want to generate a random key, right? Because you need to make sure that nobody else will be able to figure out your private key. And how do you make sure of that? Well, you're going to use some truly random number generator that generates a random value, and therefore nobody else could have generated that random value on their own. Okay? So if you're going to use just a random number generator for generating prime numbers, then you need to know, okay, can I just do a generate and test approach? Hello? So can I use the generate and test approach, I guess? That way. Okay, so I'm sure you can hear me, or it will be a good incentive for people to move forward, right? So, so prime numbers. So there is this theorem called Lagrange's theorem. It says that prime numbers occur fairly often, right? It tells you basically every log n numbers there is a prime number. Okay, so therefore, that gives you a good algorithm because you're going to generate a random number and you're going to test if it's prime. Okay, in log n attempts, you should come across something that's really a prime, and then you already have a good, fairly efficient way of checking if it's prime. Okay, so that is our algorithm. And what is the complexity? Well, you can easily show that it is like log square n, because as we said, to apply Fermat's test takes you log n multiplications, right? So if you do log n multiplication and then you have to go through possibly log n random numbers and test them each, then you're talking about log square n operations. Okay. Yeah, you might be tempted to say, okay, if n is not primed, the random number I generate is not primed, I'm going to just try n plus 1 and n plus 2 and so on. Should I do that, or should I simply generate a new random number? What should I do? What should I do? Generate a new. So what? Obviously, I did that reason, right?
Try n plus 1 and plus 2.
So why? Why should I do that?
Because among n numbers there are...
Okay, so I'll tell you it's not a good idea. So tell me why. Why it's not a good idea? N plus 1, n plus 2. Yeah.
Actually,
So you can take this as an exercise, right? Prove that, there may be arbitrarily large intervals where there are no prime numbers. Okay? So you can actually find, arbitrarily, large intervals in which there are no prime numbers. Okay? As a result, if you happen to hit on one of them, then this n plus 1, n plus 2 might keep going forever. Right? So whereas if you just regenerate, another random number, well then probabilities are on your side, and eventually you will get to something that. Yeah.
Will it not depend on how I'm generating a random?
Of course, if you're generating a cryptographic key, obviously you need to be very careful how you generate the random number, right? Because nobody else should be able to figure out and be able to get your exact random number, right? So,
Can you elaborate a little? How can I make a good random generator?
right, so you need what are called true random number generators, right? So in algorithms, we often use what are called pseudo-random number generators, right? Because they should look, statistically speaking, they should look random, right? But the fact that somebody can predict the next so-called random number from the previous one is not relevant. Whereas in cryptography, we want what is called true randomness. And you need to have true sources of randomness for generating these random numbers, right? So computers, what they do is that they often look for, there are sources of randomness. So for instance, let's say you're typing, right? And the computer can figure out, okay, how often, what is the last few digits of a nanosecond granularity clock that, what is its value as you type each of your, keys, right? You can imagine that is not something that can be, that's not really under anyone's control, right? If I look at, say, at the millisecond granularity, well, there is not much randomness, right? Because we all have a particular speed of typing, and it'll be very easy to figure out what those values are. But if I look at nanosecond level, well, I don't know. Same way, let's say we are getting the computer's getting packets on the internet, from the internet, and once again, if you look at the lowest, least significant bits of the clock, as packets arrive, that's another way to, another true source of randomness. Okay? So you have to use these sorts of things, and so in your computer, if you look at, dig into the operating system in more detail, they will have something called an entropy pool. Okay? And this entropy pool is where, these types of, random events are somehow aggregated. So if you go on your Linux machine, there is a device called /dev/random, okay? And this is actually a device into which this randomness is pooled. So if you read from /dev/random, then that'll give you truly random numbers, right? So for instance, what I usually do is whenever I go to a website, I want to remember, I want to create a password, I use this /dev/random to generate a random password, and then of course I make my browser remember that password, so that obviously I can't remember a random password, right? So I make my password manager remember that. But that's a good way of you just take this true randomness and use that to generate passwords. But what happens is you'll also find that if you keep reading this device /dev/random, you'll soon run out because there's only so much source of randomness, right? So you shouldn't keep reading. You shouldn't have applications there which are keeping on reading this dev random, okay? And Yeah, anyway. Any other questions? Okay, so, well, we know how to do, except that we have this Carmichael's numbers, and we said, well, they pose a problem. So in reality, you don't use Fermat's test. There is another test called Rabin-Miller test, which is kind of similar. It's a little bit more involved, and it doesn't just compute a to the power n, but also looks at how you got there as you do recursive squaring, and then does a more complex test, and it is guaranteed to work correctly. Okay, and it also has a provable probability of 0.75 of being right instead of 0.5. Okay, so which means that value you get a high enough probability pretty soon. So this is the last probabilistic algorithm that we are going to talk about, and in fact it's also